In this lesson, we're going to be looking at solving quadratic inequalities. With solving quadratic inequalities, they're very similar starting out to solving equations because we want to get a quadratic equation equal to 0. So we're going to do the same thing here. We want to get the 15 to the left side so that it's finally equal to 0. I would do that by subtracting 15 to both sides. So that's going to say minus 15 over here. And now it's less than 0. That gives me something I can factor. So I would take this and try to get it in factored form. The 2x squared came from multiplying 2x times x. So I know those are the first parts of the binomial. And then we find our factors of 15. This could be 5 and 3 or 3 and 5. It really just depends on what we have. So let me switch to a pencil here, because if I have 5 times 3, that would be 5x when I distribute, and on the outsides 3 times 2 gives me 6x, and together that can be a -1 if this is a -6. But if that didn't work, I would need to swap places and put the 3 here and the 5 there and do some guess and check. So this ends up working. Let me erase what we have. And now we can put in our 5 and 3 as permanent parts. So we needed a -6, remember, and a +5. That meant that was a -3. Once it's in factored form, we use that zero product property to set each factor equal to 0. So I'm going to say 2x plus 5 equals 0, and x minus 3 equals 0. This will find those x-intercepts, which will help us figure out when the inequality is less than 0. So I solve it out, I get 2x equals -5 and x equals -5/2. And then again, x equals 3. So those are the x-intercepts when it's equal to 0, but we want to know, when is the function going to be less than 0? So if I looked at a number line, this would be a -5/2 first, and then a +3 eventually. We want to know when it's less than 0. So I'm just going to put that off to the side here as a reminder. And what we have created are 3 different regions of the number line. And we're going to call these test intervals. Now, our inequality says less than, strictly less than. It doesn't have the equal to. So that's our first clue that these are going to be open circles at -5/2 and at +3. But we need to figure out which interval will the inequality be true. We do that by creating some test points. So over here, I've kind of gone through the different steps that we have, and I'm going to pick test coordinates or test points. So let's say x equals some value here to the left. -5/2 is -2.5. So I could pick any value to the left here. I might pick -4. If x is -4, I'm plugging that in just to see if it's going to end up being less than 0. You don't have to do this completely algebraically, but I'm going to at least show what I mean by that. So 2 times -4 plus 5 times -4 minus 3. All I'm looking at is what's the product going to end up being. So -2 times, or 2 times -4 is -8. -8 plus 5 is still a negative value. So I'm going to get a negative number. I don't really care exactly what that number is, but then I have -4 minus 3 is still negative. So we get a negative times a negative, which ends up being a positive. So what I'm trying to test is this interval going to be below 0? And this interval will end up always coming out positive. So that's not going to be below 0. Now we pick a point in between -5/2 and 3. A nice point to pick is 0. So if x is equal to 0, you'd plug it in and do 2 times 0 plus 5 and 0 minus 3. That would be 0 plus 5 is a positive, 0 minus 3 is a negative, so I end up getting a negative. Now the middle area is all going to be negative. Then we try the last area again, so x equals maybe positive 4 because that's to the right of 3. 2 times positive 4 plus 5 and positive 4 minus 3. That's going to be a positive value on the first factor, and 4 minus 3 is still positive on the right. So positive times a positive is positive. Now what we just found were all of the different areas where the function will be above or below the axis. And we wanted less than 0, so it's the values in between in the middle. So our solution region, we're going to write in interval notation. It would say parentheses, negative 5/2, all the way to 3, and parentheses again. We're doing parentheses because these were open circles. It was open since we did not have the equal to in our inequality. This is one method in solving an inequality. We're going to also look at that graphically. If we had this quadratic equation here, we could graph this just off our basic sketch. And what we found were the x-intercepts. So I know it's going to cross the x-axis at negative 5/2 and positive 3. If we're worried about when the function is below 0, it is the area below the axis. And we're trying to describe that. So our solution would still say from negative 5/2 to 3, but you have to consider, do we include those points or exclude them? So we're going to exclude them because they were open. We only wanted less than. So that's the same solution, just a graphical method. All right, let's look at 2. It's already set to 0. We've got everything on the left side. So let's try to factor if we can. X squared came from multiplying 3x times x, and factors of 20. Now there's a few more different factors of 20. You could do 2 and 10, 4 and 5, and see which one ends up working. Let me try 4 and 5. I'm switching to a pencil because this may be wrong. If you're used to factoring, you might be guessing and checking. So 4 times x is 4x, 3 times 5 is 15x, and there's no way that 15x and 4 are going to combine to give me a 7. So that means that those two numbers are not going to work. So let's pick some different ones. Maybe I could swap it and put the 5 here and the 4 there. So if I do that, that would be a 5x, and 3 times 4 is a 12x. 5x and 12x will give us a 7 if the 5 is negative. So that's going to work. We need a negative 5 and a positive 4. All right. So negative 5, positive 4 gives me these factors, and we can solve out to get the x-intercepts. So 3x minus 5 equals 0, x plus 4 equals 0. 3x equals 5, and x equals 5/3. X equals negative 4. So negative 4 is on the left side and 5/3 is on the right side. We want to know when the value is greater than or equal to 0. So just put that off to the side of your number line to give you an idea. If you want to do this graphically, that's perfectly fine. You want to look at this inequality that we have. Always start with one that's equal to 0. So if we had to move it around like this one, we went back to where it was equal to 0. Now this one is positive 3x squared, which means it would be going up. So if I graphed just a general parabola, it would look something like this. Not perfect, but I know that it is above 0 for all of these values here. That would mean I could close this circle in, since it does get to equal, and shade to the left, and close this circle in and shade to the right. So graphically it makes it a little bit easier. You don't have to do all the plugging in, but you do have to think a little bit more critically because you're having to look at the part where it's just equal to 0. Now you could test some points and double check that. So I could pick a point like -5, x equals -5. I'm plugging that back into our factored form. And so if I plug that in here, -5 times 3 is -15, -15 minus 5, there's another negative, so I'm going to end up with a negative times -5 plus 4 is -1. Negative times a negative is positive. That's how we got this positive area here to the left. If I tested out a value in between, like 0, that'd be 0 times 3 is 0, minus 5 is negative, and 0 plus 4 is positive. And negative times a positive is still negative. That's why it's below the axis there. We test another point to the right, so maybe x equals +4. 5/3 is not even 2 yet, so you could plug in 2, you could plug in 3, you could plug in 4, anything you want above that. So let's say I plug in 4. 4 times 3 is 12, 12 minus 5, yeah, that's still big, that's still positive. And then 4 plus 4 is still positive, and a positive times a positive is positive. That's why we're above the axis there. But we still have to finish. We haven't actually written out what is the solution yet. So our solution is our interval -∞ up into -4 with a bracket we wanted to equal to, union positive 5/3 all the way to infinity. All right, number 3. 3 has something that's just an x squared, but we still need to get it equal to 0. A lot of times students will try to just square root this and get their 3's, but they'll forget about really trying this out. So I'm going to move this over and subtract 9 so that we're following the same thing the whole time. So if I subtracted it, now it's equal to 0, and we can factor. That's a difference of 2 squares, x plus 3 times x minus 3. Your difference of 2 squares, just to remind yourself, let's put that here on a sticky note. Difference of squares was something like a squared minus b squared, and it factored into a plus b and a minus b. This looks that way because we have x squared and 9 is 3 squared. That's how we got the x minus 3 and x plus 3. Now I have the two x-intercepts to find. That's x equals -3. And this one gives me x equals +3. We've got our two values to test. positive 3. We're looking for when it's greater than or equal to 0. That means I do get to include those values. I can close in those dots. But we want to know, what is the general shape? If I go back to this one, notice I'm going back to when I've got it equal to 0. Not the very beginning, because it wasn't equal to 0 yet. So this one still is a positive x squared, which would give me a graph that's above, pointing up. So those are going to be above or greater than 0 for all of these values here. And we can find our solution here is parentheses negative infinity to negative 3 with a bracket, union, I should have put more room here, bracket 3 to infinity. You can again use your test intervals. That's fine. Our test intervals make up the 3 different sections that we have. All right, here's one section, negative infinity up to negative 3. Negative 3 to positive 3 is another interval, and then 3 to infinity. So there are 3 different test intervals.